In this video, I want to illustrate the classical theory of thin plates. So, a thin plate can be considered as almost a two-dimensional object. And I say almost because we have some kind of two-dimensional object with a small thickness. So, we have some thickness, and the thickness of the object is h, and h is smaller than the bidimensional object that we have here. So the extension along the z-axis is much smaller than the extension that we have on the xy plane. So at first I'm going to introduce some well-known formulas in the theory of elasticity. So we consider the small change in the internal energy. So this can be thought of as the elastic energy per unit volume of the object. So it's associated with the object, and it's given by a summation over I and j of sigma ij d epsilon ij, where epsilon ij is the strain tensor. So in this case, I'm using the letter epsilon to denote the strain tensor, and here we have the stress tensor if you want. So we are summing over I and over j. This is the increment in the internal energy, or let's say elastic energy per unit volume, and there are also other possible names that we can use, but never mind. You have to understand that this is the infinitesimal energy per unit volume associated with this object. And if you want, you can also write it in different manners. If you sum over I and over j, you have sigma xx d epsilon xx. So you can either write sigma 1 d epsilon 1 or sigma xx d epsilon xx. And I hope you all can follow what I'm saying here. And since we are considering thin plates, we are only interested in the deformations and the stresses, strains in the xy plane. So we are not considering deformations that occur in the z direction. So we only have x and y, and therefore here this summation is performed like this. We have sigma xx d epsilon xx, sigma yy d epsilon yy, and then we have plus twice sigma xy d epsilon xy. So this is equal to sigma xy d epsilon xy plus sigma yx d epsilon yx. So due to the symmetry of these tensors, this summation here can be written like this with a factor of 2. So it can be compactified like this. Now there are constitutive relations between strains and stresses, and in particular strains along the x-axis, epsilon xx, are related to sigma xx, so stresses along the x-axis, by means of this parameter E, the Young modulus, and then also they are also related to the stresses sigma yy by means of this other parameter nu, which is divided by E. So you can think of this in the following intuitive manner. So if we consider stresses along the x-axis, of course those stresses will cause some kind of deformations and therefore strains. But on the other hand, so you can consider some kind of tube, for example. So if we stretch the tube along its x-axis, let's assume that this axis here, which is the axis of the tube, or the cylinder, you can think of this as a cylinder. If we have stresses along the x-axis, then of course the length of the tube will increase. But if the length of the tube increases, it is intuitive to think that the diameter of the tube will decrease to preserve the volume. So if this dimension here, if the diameter of the tube decreases, you can think that there are also some stresses occurring in a perpendicular direction, and we think of that as sigma yy. So there is a relation between sigma yy and epsilon xx. In particular, if there is some stress in the y direction, in the perpendicular direction, the strain along the x direction will decrease. And in general, if sigma goes in the other way, in the other direction, so this is the positive direction for sigma, sigma yy, then the cylinder will, the radius of the cylinder or diameter of the cylinder will increase, and therefore its length will be contracted. It will decrease. So this constitutive relation keeps track of these considerations here. So this is just some intuition. And similarly, along y, so epsilon yy is equal to 1 over e sigma yy minus nu sigma xx. So this relation is perfectly symmetric with this one here. And then we have epsilon xy, which is equal to 1 plus nu over e sigma xy. So you can take this for granted. Epsilon xy is only related to sigma xy. These are related to shears. So these are related to shear stresses. And basically here you have a relation between the stresses and the strains. And you can also invert these relations to find sigma xx, sigma yy, and sigma xy with respect to the strains. So if you do that, this is just some simple algebra. Sigma xx can be written as e over 1 minus nu squared epsilon xx plus nu epsilon yy. Then you have sigma yy equal to e over 1 minus nu squared epsilon yy plus nu epsilon xx. And of course, the last one is quite trivial. We have sigma xy equal to e divided by 1 plus nu epsilon xy, like this. Why are these relationships important? Well, because now we can substitute the expressions here, and then we can carry out this integration. We can integrate to find u. So in particular, du can be rewritten like this. We have e over 1 minus nu squared epsilon xx d epsilon xx plus nu epsilon yy d epsilon xx plus epsilon yy d epsilon yy plus nu epsilon xx d epsilon yy plus 2 1 minus nu epsilon xy d epsilon xy. So we can write it like this. Now you can also see that we can put this one together with this one, so they can be written as nu, and then we have the differential of epsilon xx epsilon yy, and we can perform an integral. So we can integrate to find the energy per unit volume up to a constant. So when we integrate, we also get a constant which can be added to the energy, but we are not interested in that constant. We have e over 1 minus nu squared. Then you get epsilon xx squared over 2 when you integrate this. And then you have plus epsilon yy squared over 2 when you integrate this. Then you have plus nu epsilon xx epsilon yy plus 1 minus nu epsilon xy squared when you integrate this one, and this comes from the integration of these two together. So when you integrate the differential of epsilon yy epsilon xx, and now we have to find a way to express these strains in another way in terms of the deformations. And let me remind you the expression of the strain tensor. The strain tensor epsilon ij, we have derived it in a previous video. It's a tensor, and it can be written like this: 1 over 2 derivative of the deformations ui with respect to xj plus derivative uj with respect to xi, plus you also have a quadratic term dul with respect to xi, dul with respect to xj, and this quadratic term can be neglected if the deformations are small. So we are going to consider this assumption. So we are going to neglect such terms, and ui is the vector of deformations. So it has three components: u, v, and w. So u and v are the deformations on the xy plane, whereas w is the deformation along the z-axis. So if we consider our thin plate, so at first, let's assume that we can see the cross-section of the plate. So for example, this is the z-axis, and this is the x-axis. This is h, the thickness of the plate. Well, when this gets deformed, the plate can, for example, deform like this. So there are some displacements along the z direction. So for example, this is w at a certain point, and therefore we cannot really disregard this w here. What we are going to disregard are the strains epsilon zz approximately equal to 0, and also sigma zz approximately equal to 0. So these are approximations, of course, but this is according to the classic theory of thin plates. Now, from this formula here, we can write epsilon xx. So this will just give us du over dx, because we have 1/2 du over dx plus du over dx, which is of course equal to du over dx. Similarly, epsilon yy will give you dv over dy, and epsilon xy will give you 1/2 du over dy plus dv over dx. Now, let me tell you that there is a relation between the deformation w, and so remember that this is in the z direction, and the deformations u and v that occur on the plane. And let me give you the insights regarding this. So we can consider this sketch. So at first, let's assume that there is no deformation. So this is the plate, and remember that we are seeing a cross-section of the plate, and this is the thickness h, which is small compared with the other dimensions. When the plate gets deformed, let's fix this point, for example, and let's consider something like this. So we get something like this. This is the deformation of our plate. Well, there is a small angle that is created here. We can call it theta. So this angle here is small because we are considering small deformations. And if you think about it, theta is also almost equal to the tangent of theta because the angle is small. And if we enlarge this small zone, well, here the increment in this triangle here, where we have this angle theta, is a small change in w. So since this is the z-axis, there is a displacement dw here, and this length here is dx, as we said, and therefore theta, the angle theta, is approximately equal to dw dx. So this is also the tangent of theta, right? Because theta is small. And if we take a look at, for example, this, if we take a look at this point, this will get displaced in here. And if we consider this small triangle, we also have the angle theta here. So we can obtain this displacement. And if you think about it, this is the displacement along the x direction, right? Because This is the x-axis, and in this case the displacement is negative and this angle is positive, so we get a minus sign. We have to multiply the tangent of this angle, so it's approximately coincident with the angle itself, so we have minus dw dx, and then we multiply by this length of this side of the triangle, which is equal to h. To be precise, h in this case would be the distance between the neutral plane, and I will explain more in detail what that is, and the top of the plate. I have already used the symbol h to denote the thickness of the plate. To be precise, it is not exactly the thickness of the plate. If you want a more precise theory, you could as well think of it as the thickness of the plate if the so-called neutral plane is at the bottom of the plate, but usually the neutral plane is in the middle of the plate. Therefore, this would mean that the h that I'm using here would be half of the thickness of the plate. I will give you some more details in a moment. Anyway, minus dw dx times h. What is that? Well, that is equal to u, the first component of the vector ui, which is given by u, v, and w. Also, please do not get confused between this u and the energy per unit volume, which is a capital U. So this is a capital U, and the other one is a lowercase u. But at the same time, we can also say something similar for v. V will be equal to minus h dw dy. So this is the partial derivative with respect to y. Now, this v here and this u written like this, they are displacements that are calculated on the top of this surface here. To be more precise, in general, when you consider deformations of plates, well, you calculate the generic displacement for a generic height. By height, I mean the generic location inside this plate. Basically, h is small, but we can calculate these displacements for a generic height, and we can call that z instead of h. So, for example, u would be minus z times dw dx, and similarly v would be minus z dw dy. Now, I will not write these expressions, but it is just to highlight the fact that if you measure z from the so-called neutral axis, so basically the neutral axis is the axis where epsilon xx is equal to epsilon yy, which is equal to 0. So the strains are 0, and also the stresses are there 0 on such an axis where you start measuring z. So z can range from minus h over 2 to h over 2 if you really want to be precise. And therefore you can use these formulas where you replace h with z measured like this. But in this case, I don't want to do all these details. I don't want to write down all these details. So I will consider basically only the formulas for the deformations that we have on the top of the plate. And also when we replace this function here and this function here, so these formulas, when we replace them in the expression for deformations and then finally in the energy per unit volume, then we will have to take the variation of an action and we will obtain some equations of motion which are very general, and they are not really dependent on whether you put h here or you put z. What changes, of course, would be the energy, because when you have the energy u, you have to integrate it over d3x if you want to get the energy in the total volume. So you have to integrate over the volume, and one of these differentials will contain dz. So we will also have to integrate this over dz, and the integral would be performed over this variable h, which would be raised to the second power, and you have to replace h with z to be precise, and then you can carry out the integral. You have an integral of dz, and then you have z squared, so you will get z cubed over 3, and the integral is performed from minus h over 2 to h over 2. So you get something like that, and you can carry out the integration, but the form of the expression that you get is basically the same up to a constant, a multiplicative constant in front of the energy. So these are just some details that are not really too important, because as I said, I want to focus on the derivation of the equations related to the deformation of the plate. And now that we have these two relations, they can be substituted in here to obtain these strains in terms of derivatives of W. So this is important. So if you do that and you substitute the strains into the expressions for the energy here, you get an expression for the energy which is written in terms of derivatives of W, the displacement along the z-axis. This can be done, it's straightforward. For example, I did it with MATLAB, and if necessary, I will attach the script to the video. It's nothing really difficult, it's just a bunch of simple calculations, but U can be written like this. So the energy is minus E h squared divided by 2 nu squared minus 1, and then we have partial of W, so the second derivative of W with respect to x squared plus second derivative of W with respect to y squared plus, and then we can write twice second derivative of W with respect to x and with respect to y, and this is squared, and then we have 2 nu second derivative of W with respect to x squared, and then we have the second derivative of W with respect to y, so y twice, and then finally we have minus second derivative of W with respect to x, with respect to y, and this is squared. And that's the energy. So if necessary, this term here could also be written as the determinant of the Hessian matrix of W, but it's not really important. What we seek to do now is we want to take the variation of a certain action, and in particular in this case we assume that there are no external forces, so the overall energy is the integral of the energy per unit volume over the volume, so we have d3x, and we consider this to be the action, really, so our action. If there are external forces, then you have an additional term that you have to consider, but in this case what we consider is only this part of the action, so we consider only internal stresses and strains, and we want to find the equations of motion, if you want, by minimizing this action. So we take the variation of that and we set it equal to 0. Now the variation is not difficult to carry out. We can neglect this first constant since we have to set it equal to 0. It's not important. And then we have an integral. When we take the variation of this first term, we have twice partial derivative, the second derivative of W with respect to x, and then we have the variation of this same term, and the variation can be put inside the derivative, so we have the second derivative with respect to x of the variation of W, and similarly this term here you have plus 2 d squared w dy squared d squared dy squared dw. Then you have plus 4, because here you have also a factor of 2, second derivative of w with respect to x with respect to y, second derivative with respect to x with respect to y of delta w, like that, and then you have plus 2 nu, and when you take the variation of this term, you get second derivative with respect to x squared, variation of w, d squared w dy squared, plus, let me go below, plus, you also have the variation of this term, so you have d squared w dx squared d squared dy squared delta w minus, and then you get 2 d squared w dx dy variation, or actually we can put the variation inside the derivative, so we have d squared dx dy delta w. We close this bracket, and then we also have to close this bracket here, and you have d3x, and you have to set it equal to 0. Now at this point we can carry out an integration by parts, and we can do it twice. So for example, when we integrate this term by parts twice, we get that this operator will be in front of this term, so we get minus. After one integration by parts, you get a minus, and then after another integration by parts, this minus will become a plus. So you have d4 dx to the 4 w dw, and similarly, you can integrate this one by parts to get d4w dy to the 4th dw. And similarly, you can integrate this one by parts. You understand the idea, and you also have to integrate these terms by parts. So once you do that, you get, let me write it here, integral, you have 2 d4w dx to the 4th plus d4w dy to the 4th plus 2 d4w dx squared dy squared. This multiplies delta w, and then you have plus 2 nu, and then you have the terms in here after you integrate them twice by parts. So when you integrate this one, you get d4w dx squared dy squared, and this multiplies delta w, of course. And similarly here you get plus d4w dx squared dy squared, which multiplies delta w, so we can basically put a factor of 2 here, and then you get minus, so you get minus actually we have a factor of 2 here, d4w dx squared dy squared delta w, like this, and then of course you also have d3x equal to 0. Now you can see that this variation here will be 0 because those two terms cancel, and now we have this term which multiplies this variation, and since this variation here is arbitrary, we have to set this equal to 0. So we get basically the following. This equation can be written as d squared dx squared plus d squared dy squared w equal to 0. So if you square this, basically you get the operator d4 dx to the 4th plus d4 dy to the 4th plus twice d fourth dx squared dy squared. And this can also be written as the Laplacian squared. So this is the Laplacian here in 2 dimensions, because we are considering only functions of x and y. W depends only on x and y. And you have to square this, and then you apply this to w equal to 0. So this equation can also be written as nabla to the 4 w equal to 0, which is the final equation that we obtain. And this is the equation related to the classical theory of thin plates.